Welcome to The Deep Dive. Today, we're diving into a topic that might sound a bit pessimistic, maybe, but it's absolutely crucial for understanding pretty much every digital service you use.
Right.
We're talking about the trouble with distributed systems. You probably think of your computer as, just one thing. It either works or it doesn't.
Simple. Yeah.
But what happens when you've got thousands of computers all trying to talk to each other across a network?
It gets messy, Reen.
It gets really messy. And what's fascinating, I think, is how we move from that sort of idealized world of a single machine where things are mostly deterministic. You do something, you get the same result.
Predictable.
Exactly, predictable. Into the unpredictable reality of the physical world amplified across a network. So our mission today is maybe to explore all the different ways things can go wrong.
All the weird ways. All the weird ways. And what engineers actually do to build reliable systems out of these inherently unreliable pieces. Think of it as kind of uncovering the hidden complexity that makes your favorite apps work, or sometimes, glitch out. The fundamental shift from single computer perfection to distributed system reality.
Okay, so let's unpack that a bit. On my laptop, right, if something goes badly wrong, I might get the blue screen of death. It just crashes.
Great, total failure.
And you said that's often deliberate, like better to crash than give bad data.
That's often the philosophy, yeah. Better safe than, essentially stop everything rather than risk incorrectness.
So what's the fundamental change when we connect lots of these together in a distributed system?
The absolute core difference is this idea of partial failure.
Partial failure.
Yeah. In a distributed system, some parts can be broken, maybe in really bizarre and unpredictable ways, while other parts are humming along just fine.
Okay, so it's not all or nothing anymore.
Not at all. And that makes the whole system inherently non-deterministic. You can't always predict exactly how it'll behave. There's that great anecdote from Coda Hale, where he talks about everything that can go wrong. Network cables cut, power outages, sure, but also like a hypoglycemic driver smashing his Ford pickup truck into a DC's HVAC system.
Wow. Okay, that's specific and vivid.
It really paints a picture of the kind of real-world chaos engineers have to think about. It's not just clean, theoretical failures.
That's wild. So how does this thinking differ from, say, supercomputers? I always kind of pictured them as these massive, interconnected, maybe more robust systems.
Well, it's a different approach. If you think about the bigger picture, supercomputers often used for like big scientific simulations. They typically handle failure differently.
How so?
If one part fails, they often just stop the entire job running across the whole cluster.
Okay.
Then they'll fix the problem and restart the computation from a previously saved checkpoint. So they essentially escalate that partial failure back to a total failure for the job.
But you can't do that with, like, Google search or your bank's website.
Exactly. For internet services, that kind of downtime is just unacceptable.
Yeah.
We need these things to be online 24/7, right? Even though they're often built using, standard commodity hardware.
Which fails more often than specialized supercomputer parts, I guess.
Generally, yes. So this is where that core idea comes in. Building reliability from unreliable components. It's actually an old concept in networking. Think about TCP making IP reliable.
Right, retransmitting lost packets and all that.
Precisely. TCP adds guarantees on top of the less reliable IP layer. But, and this is important, there are always limits. You can layer reliability, but you can't perfectly eliminate the underlying uncertainty.
So even if you have just a few machines talking to each other, you can't just assume everything will be fine. No crossing your fingers.
Definitely not. In distributed systems, a healthy dose of suspicion, maybe even pessimism or paranoia, it actually pays off.
Designed for failure from the start.
You have to. And you even need to test for it deliberately. That's what things like Netflix's Chaos Monkey are all about, intentionally breaking things in production.
But to make sure you can handle it.
Exactly, to build that resilience. It's about embracing the potential chaos to ultimately control it better. 2, the unreliable network. The great unknown.
Okay, so designing for failure is key. And it feels like the first place things get really unreliable is the network itself, right? That connection between all the computers.
Absolutely. The network is the backbone, but it's also, well, a bit of a trickster, as you put it.
You send a message out.
And you honestly have no guarantee it will arrive, or when it might arrive, or if you'll ever hear back.
So you're just shouting into the void sometime.
Pretty much. We're talking about like these asynchronous packet networks. That's the internet, that's most data centers. Data gets chopped up, sent out. Maybe it gets there, maybe it doesn't.
And if you send a request and you don't get a response back?
You're completely in the dark. You just don't know why. Was your request lost? Did the other machine crash? Was a response lost on its way back? Or is everything just really, really slow right now?
So you can't tell the difference between broken and slow.
Not easily. The only real tool you have in that situation is a timeout. You wait a certain amount of time, and if you hear nothing,
You assume it failed.
you assume it failed. But that's just an assumption.
And what's really wild is that these network problems, they're still super common, right? Even in fancy data centers.
Oh, absolutely. Studies show network faults happen like monthly,
Mm-hmm.
and a huge chunk of them are actually human error misconfigurations, typos.
Oops.
Exactly. And then there are the truly weird things, like I remember reading about sharks literally biting undersea fiber optic cables.
Sharks. Okay, add that to the list of things that can break your app. And you also mentioned just because data can flow one way doesn't mean it can flow back.
That's another fun one. Asymmetric reachability. Link might be fine sending, but broken receiving. So yeah, network unreliability is just a fundamental fact you have to deal with.
Which leads to that timeout problem you mentioned. How long do you wait?
And that's a critical tuning parameter.
Hmm.
A long timeout means your system is slow detecting actual faults. Things stay broken for longer.
A short one.
A short one risks declaring a perfectly healthy node dead just because it was temporarily slow, maybe due to network congestion or a brief pause.
And it could make things worse.
Much worse. It can lead to these cascading failures. You mistakenly kill off nodes, putting more load on the remaining ones, which then slow down, causing more timeouts.
Hmm.
It's a dangerous spiral.
Yikes. Okay, so given all this, why can't we just build networks that guarantee delivery times? Like, promise a maximum delay. You mentioned old phone networks could do that.
Right. The old telephone system used circuit switching. When you made a call, you got a dedicated physical circuit end-to-end with reserved bandwidth.
Like your own private lane on the highway.
Exactly. And that guarantees a bounded delay. It's synchronous. But the internet and modern data center networks use packet switching.
Everything gets chopped up and shares the roads.
Precisely. It's optimized for bursty traffic.
Yeah.
Lots of users sharing the capacity. This is way more efficient, uses the resources better, makes it cheaper.
But the downside is,
Queues build up. Packets can get delayed,
Yeah.
sometimes for unpredictable, potentially unbounded amounts of time. So it's a cost and efficiency trade-off, fundamentally, not some immutable law of physics. We chose this trade-off. 3. The fickle clocks. A time-sensitive minefield.
okay, so the network's a mess. Messages get lost, delayed. But even if a message does get through, there's another problem, right? Knowing when things happen. You mentioned clocks.
Ah, yes, time. Another seemingly simple concept that gets incredibly complicated in distributed systems.
How so? My computer clock seems fine.
While your computer clock is one thing, but every machine in a distributed system has its own physical clock device, usually a quartz crystal.
Yeah.
And none of them are perfectly accurate. They drift.
They drift, like they run slightly fast or slow.
Exactly. And they drift at different rates. So even if you synchronize them perfectly at one moment, they'll start to diverge almost immediately.
Huh. So we try to sync them, right, with NTP.
We do. Network time protocol tries its best. But think about it. It relies on that same unreliable network we just talked about.
Ah, right. Network delays affect the sync accuracy.
Totally. Plus, you have firewalls potentially blocking NTP traffic. The clocks themselves can be forced backwards or forwards by administrators. Sometimes NTP servers are misconfigured.
It sounds like a nightmare.
And that's just for time-of-day clocks, the ones trying to tell you, what time it actually is according to UTC.
Are there other kinds?
Yeah. There are also monotonic clocks. These are simpler. They just guarantee they always move forward on a single machine, like a stopwatch. They're good for measuring durations locally, like for timeouts.
But not for figuring out event order between machines.
Not reliably, no, because they don't correlate to any external reality or to each other across nodes. And time-of-day clocks, with all their issues, quartz drift, sync problems, and, let's not forget leap seconds.
Leap seconds. I've heard those cause problems.
They have famously crashed many large systems that weren't prepared for that little hiccup in timekeeping.
Okay, so clocks are unreliable. What does that mean for, say, a database where multiple people might be writing data at roughly the same time?
This is where it gets really dangerous. Imagine a common strategy called last write wins, or LWW.
Okay, whoever wrote last, their data is kept. Seems logical.
Logical if you have a perfect shared sense of last. But if you rely on potentially skewed time-of-day timestamps from different machines,
Uh-oh.
yeah, you could have two clients write. Client A writes, then client B writes a fraction of a second later. But if client A's clock is slightly ahead of client B's clock,
Client A's write might look like it happened after client B's.
exactly. So client B's write, which actually happened later, gets overwritten. Data just silently disappears. It breaks causality.
Wow. So LWW with wall clock time is risky.
Very risky. It can't reliably distinguish truly concurrent writes from causally ordered ones.
Yeah.
It's like seeing effects before causes.
Is there a way around this?
Well, some very sophisticated systems, like Google's Spanner database, tackle this head-on. They use something called true time.
True time.
Yeah, instead of giving you just one timestamp, their API gives you a confidence interval, a time range earliest, latest, where the true time almost certainly lies.
Okay, so it acknowledges the uncertainty.
Precisely. And then, critically, when committing a transaction that depends on time, they deliberately wait until they know the latest time in that interval has definitely passed everywhere.
They wait out the uncertainty.
Effectively, yes. It ensures causality is maintained, even with clock skew. That's why they need super precise atomic clocks and GPS receivers in their data centers. For simpler ordering needs, though, logical clocks, basically just event counters, are often a much safer bet than relying on wall clock time. 4. The unexpected pauses. When your server
Just. Okay, unreliable networks, unreliable clocks. What else can go wrong? This sounds like building on quicksand.
Well, here's another fun one. Imagine you have a system where one node is elected the leader for a particular piece of data.
Right, like the primary replica in a database partition. It handles the writes.
Exactly. And to prove it's the leader, it usually gets a lease, basically permission to be the leader for a certain period. It has to renew the lease before it expires.
Makes sense, keeps things orderly.
Usually. But what if that leader node just pauses, suddenly stops executing for a while, maybe without even realizing it?
Pauses, like the whole process just freezes.
Yeah, it might sound crazy, but it's totally possible for a process or a thread to be paused for tens, hundreds of milliseconds, maybe even seconds, or in extreme cases, minutes.
Minutes. Why would that happen?
All sorts of reasons. A big one is stop the world garbage collection in languages like Java or Go. The runtime just freezes everything briefly to clean up memory.
Okay, I've heard of GC pauses.
Then you've got virtual machine stuff. Maybe the VM gets suspended or migrated to another physical host. Or just the operating system deciding to run something else for a bit, content switching. Or waiting for slow disk I/O. Or even swapping memory to disk, paging.
Wow, okay. Lots of hidden pauses.
And the application running inside might be totally oblivious. It just wakes up later and tries to carry on where it left
Yeah,
off.
let's connect the dots. The leader pauses.
Its lease expires while it's paused.
So the system elects a new leader correctly.
The new leader starts accepting rights.
And then the old leader wakes up.
Exactly. Wakes up, checks its memory, thinks, hey, my lease was valid when I last checked,
Yeah.
and maybe starts accepting rights again, thinking it's still the leader.
Oh, no. So you have two leaders writing potentially conflicting data. That sounds like guaranteed data corruption.
It absolutely can be. The source material gives a really clear example of this breaking a distributed lock system, where two clients think they hold the lock simultaneously and corrupt a shared file.
So the big takeaway here is
It's a profound one. A node in a distributed system cannot necessarily trust its own judgment. Its internal state, its memory, its perception of time, it can all be stale and dangerously out of sync with the actual reality of the system.
that's unsettling. How do you prevent that? How do you stop these zombie leaders from causing damage after they wake up?
Okay, so this brings us to a really important safety mechanism, a technique called fencing tokens.
Fencing tokens, like building a fence around the data.
Kind of. Every time the system grants a lease or a lock, it doesn't just say, okay, you're the leader. It also gives the leader an incrementing number, the fencing token. Think of it like a version number for the leadership.
Okay, so leader 1 gets token 10, then if it fails and leader 2 takes over, leader 2 gets token 11.
Exactly. And here's the key. Any write request the leader sends to the actual data storage must include its fencing token.
Uh-huh.
So the storage service itself gets involved. If our old leader, with token 10, wakes up and tries to write something after the storage is already processed a write from the new leader, with token 11.
The storage sees the older token and just says, nope.
Precisely. It rejects the write because the token is stale. It ensures that actions from a previous era of leadership can't corrupt the current state. The genius is it pushes the enforcement to the resource itself, which can see the sequence of tokens, rather than relying on the potentially confused leaders. V, establishing truth in an unreliable world. Models and guarantees.
Okay, fencing tokens, that's clever. But stepping back, we've got unreliable networks, flicky clocks, processes that take unexpected naps. It really feels like a single node in these systems can't know anything for sure.
That's not far from the truth.
So how do we build reliable services on top of all this uncertainty? How do you even establish what the truth is?
Well, the fundamental way is to move away from relying on any single node's perspective. In distributed systems, truth is often defined by consensus among a majority.
The majority rules.
Exactly. We use quorum systems. This means critical operations, like committing a transaction or confirming a write, require acknowledgement from a minimum number of nodes, a quorum.
So if one node is down, or paused, or has a crazy clock, the system can still agree on the state as long as enough other nodes are okay.
That's the core idea. It reduces the dependence on any single point of failure or unreliable component.
Okay, that makes sense for nodes that are unreliable but, like, trying to be helpful. What about nodes that might deliberately lie? Send fake messages or act maliciously?
Now you're entering the realm of Byzantine faults.
Byzantine, like the empire.
Exactly. It comes from the famous Byzantine generals problem, a thought experiment where loyal generals need to agree on a battle plan, but they have to communicate via messengers, and some of the generals might be traitors trying to sabotage the plan.
So nodes that can do anything, even act maliciously, that sounds way harder to deal with.
It is significantly harder. Designing systems that are Byzantine fault-tolerant, BFT, is very complex and has a performance cost. It's absolutely critical for things like cryptocurrencies. Bitcoin relies on BFT or maybe aerospace systems.
But not typically for standard web services.
Generally not. Most data center systems make a simplifying assumption. Nodes might crash, they might be slow, their clocks might be off, packets might get lost. But they don't assume nodes are actively malicious. They assume nodes are unreliable but honest.
Okay. Still, you might get weird behavior from bugs or misconfigurations that looks like lying.
Right, and we do guard against weaker forms of that, like using checksums at the application level to detect corrupted data, or having NTP clients be skeptical and ignore time sources that seem way off from the others.
So, given this inherent chaos, how do engineers even start to design algorithms? It can't just be trial and error. There must be some way to reason about it formally.
Absolutely. This is where system models become incredibly important. They are abstractions, simplified descriptions of the kinds of failures an algorithm is expected to handle.
Like defining the rules of the game.
Exactly.
Yeah.
For example, the model might specify assumptions about network behavior, like are message delays bounded or unbounded, or assumptions about clocks, or assumptions about node failures. Can they just crash, or can they do anything? Byzantine.
And what model do most typical internet systems assume?
We mostly work within the partially synchronous model. This acknowledges that most of the time, networks and processes are reasonably behaved, but occasionally delays or pauses can become arbitrarily long, effectively unbounded.
So it captures that mix of usually okay, but sometimes really bad.
Precisely. And we usually combine that with crash recovery faults, meaning nodes can crash, but might eventually restart and rejoin the system.
Okay, so you have the model. Now, how do you define if your algorithm is actually correct within that model? What does correct even mean here?
Great question. We define correctness using specific properties that the algorithm must satisfy. And these properties usually fall into two main categories: safety and liveness.
Safety and liveness.
Well, safety properties essentially mean nothing irrevocably bad ever happens. If a safety property is violated, the system is permanently in a bad state, and you can't undo it.
Like data corruption. Or that fencing token thing, ensuring uniqueness.
Exactly. Uniqueness of generated IDs, avoiding double spending, ensuring linearizability in databases. These are all safety properties. They must always hold, no matter what failures occur within the model.
And liveness.
Liveness properties mean something good eventually happens. There's always hope. For example, a request that's submitted will eventually receive a response, or a node that crashes will eventually recover.
But eventually, could be a long time.
It could. And liveness properties often have conditions attached, like assuming the network eventually recovers, or if a majority of nodes do not permanently crash. So a system might temporarily fail to provide a response, violating liveness, but it should never, ever return an incorrect response, which would violate safety.
So safety is always, liveness is eventually, maybe.
That's a good way to put it. This distinction is incredibly powerful. It helps engineers design algorithms that prioritize safety above all else, while still aiming for liveness under reasonable conditions. It allows building robust systems despite all the underlying troubles.
Wow. Okay, this has been quite the journey into the weeds of distributed systems, networks losing things, Clocks lying, servers just vanishing for minutes.
It's a bit mind-bending, isn't it?
It really is. It makes it so clear that building software for lots of machines talking together is just fundamentally different from coding on a single predictable computer.
And that core concept of partial failure is really the heart of it all. Detecting those failures is hard. Recovering is even harder when you don't have shared memory or, a single source of truth.
Yeah, it definitely makes you appreciate systems that can just run on one machine.
It does reinforce that idea. If you can avoid distribution complexity, it's often simpler and safer.
But as you pointed out, we need distributed systems for
Yeah,
fault tolerance, right? So one machine failing doesn't take everything down.
exactly. And for low latency, putting data closer to users around the world, and just for sheer scale handling traffic that no single machine could ever cope with.
So it's always a trade-off. We accept this unreliability and complexity to get those benefits. We can try to make networks and clocks more reliable.
But that usually costs more or uses resources less efficiently, like that circuit switching example. There's no free lunch.
We've definitely focused on the trouble today, the
Yes.
problems, but it's also amazing that engineers have found ways to build incredibly reliable services on top of all this mess.
Absolutely. And those theoretical models we talked about, partial synchrony, safety, liveness, even though they're simplifications, they are so valuable. They provide a framework for reasoning systematically about these problems, complementing all the real-world testing and experience.
It forces a certain rigor, I guess.
It really does. It's a challenging field, but that's what makes the solution so interesting.
So, thinking back on our conversation, what really stands out to you? For me, maybe it's just that next time my favorite app glitches or, a video call
It produces a
stutters.
bit more sympathy.
Yeah. Or at least a new appreciation for the sheer amount of engineering complexity being juggled behind the scenes just to keep things running most of the time. It's kind of heroic in a hidden way.
It really is. Fighting entropy one packet at a time.
And maybe if you listening are curious about how engineers actually solve these problems, the algorithms, the protocols like Paxos or RAT, well, that's a whole other deep dive just waiting to happen.